After mid-ocean ridges, we go to subduction zone. Serge works in Montpellier and has been spending his whole career on subduction.
Thank you, Laurent. So I will focus on another aspect of the work of Xavier on another kind of plate boundaries, which are the subduction zones. First, I would like to start my presentation with because I had the opportunity to work for a few years or a decade with Xavier Le Pichon on a project in Japan, and so I will start with the example of Japan and that part of his work. And then, I will focus on the megathrust events. So the megathrust events are the, in the subduction zone, the plate boundary, the interface between the upper plate and the subducting plate is here. And one part, the shallow part of this interface is what we call strictly the seismogenic zone that produces the seismicity, and I will focus on these type of events and not the others. Okay, and after an introduction in memory of Xavier, I will present you an overview of the diversity of the seismogenic behaviors based on the megathrust events that occurred since 1900. And then I will try to put them in the context of what we know about the paleo events, historical events prior to 1900, and also the geodetic data, how it fits, where are the conflicts. So this is new and not the others. So to start the history, back to Japan. In the 80s, most Japanese seismologists considered that the highest risk short-term in Japan concerned the Nankai area in the southern part of Japan, based on the assumption of what we call characteristic earthquakes that occur again and again and with about the same characteristics, And the assumption came from the fact that in the northern part of Japan, of Tohoku, for example, there were no magnitude more than 8 or 8 or more that occurred since 1900, except in the northern, in very far north. And yeah, okay. So. But in the southern part of Japan, there were 3 events, 3 magnitude more than 8 events that occurred during the same period of time, and that ruptured the whole area, but not exactly the full area, all the southwest Japan, except this region called Tokai area. In addition to that, and yes, these 3 events occurred within 6 years. It was a sequence, a series of events that occurred during 6 years. And in addition to this, in 1854, there were a major cascade of events that started in Tokai area and that ruptured all this area, including Tokai, within 32 hours. Okay. And based on this, it was considered in the 80s that the Japanese population were warned for the Tokai earthquake. And this is the context of the project that was led by Xavier Le Pichon in the middle of the 80s, in collaboration with the Japanese. And at the same time, it was coincident with the round trip, the world round trip of the Jean Charcot. This is not the Jean Charcot, this is the Nadir, but there were also a first cruise in 1984 with the Jean Charcot and in 1985 with the Nadir, and around the world. And we spent 2 months surveying the Japanese trenches and then focusing in the Tokai area, especially in 1989. So you see here some pictures from that time, you know, and with the book work by Xavier on the Kaiko project. Kaiko means trench in Japanese. So we explored the deep trenches around Japan. And you see here some people at that time, you know, here is the chairman that did not change much. And here is the team some years after, you know, with Xavier Le Pichon, who worked in this project. And we also took the opportunity of the Nautil submersible. For the first time, it was used for science, you know, and we were able to explore the Japanese trenches. 10 years after, a major event, not so huge in magnitude, but terrible in terms of damages, occurred in Kobe. It was not what we call a subduction event, strictly speaking, because the fault that ruptured was a strike-slip fault on land, above the subduction plate boundary, but there were tens of thousands of victims and thousands of deaths at that time, and the population in Japan was really shocked by this event. And very soon after, the Japanese scientists decided to deploy a lot of instruments on land to monitor the deformation of the Japanese islands. So it was a real change in mind at that time, and very soon after this event, as you can see, the density of seismometers, high sensitivity seismometers, and so on, were installed everywhere. Xavier Le Pichon at that time took that opportunity to use these new data with his group, Stéphane Mazzotti and Pierre-Henri, and also some Japanese colleagues. And they modeled the deformation of the upper plate, considered as an elastic body, you know, and they modeled the deformation of the upper plate, considering that the two plates are fully locked, and they compared the deformation that they would expect with those that was measured by the GPS stations. And their conclusion was that they confirmed the strong mechanical coupling in the southwest Japan, but they also confirmed that there were a full mechanical coupling offshore Tohoku in northeast Japan, which was something really new for the scientists at that time, you know. And 10 years after, as everybody knows, the Tohoku earthquake occurred. and it was devastating. In addition to the shake and to the tsunami that was generated during this event, as you know, the nuclear power plant was totally damaged, and this is it became something known in the whole world, and the Nankai margin, the southwest Japan margin, is still quiet. Just to remember, a year before that huge earthquake, this was the official map of the probability of ground motion in Japan. You know, and as you can see, the highest risks were weighted in the southern part, not much in this area. So, the Japanese government should admit that we were not able at that time to really reliably predict a major event. A few months ago, there were moderate, large, but not so large earthquake that occurred in the northern part of Japan at the boundary between Tohoku area and the Hokkaido. And in this area, this is the high slip asperity of that area last December. And very soon after, the government warned the population about the possibility of a mega earthquake that could follow in this area based on what happened of Tohoku 15 years ago. So, back to Xavier Le Pichon, he mentioned in his book, the last book he published, he mentioned the fact that based on his experience at the Lallemand, he became aware of the hidden parameters. Mathilde just talked about one of the hidden parameters concerning the heat flow. You know, the prediction of the heat flow on both sides of the cooling crust on both sides of the ridges. The predicted differs from those that is measured, and this is they discovered that the main hidden parameter was the hydrothermalism. So if we look at the hidden parameter in the subduction zone in the occurrence of earthquake, the main parameter is the time of observation, and there are many other hidden parameters that we search also. Okay, but I will not cover all. So, what should we do? We need to explore all the parameters that could improve probabilistic models. For that, we need to collect data from historical earthquakes, but not only instrumental ones. We need paleoseismology, marine paleoseismology, because the subduction zones are generally offshore. The seismogenic zones are generally offshore. And we need to collect data about the seismogenic zone interface, a lot of data to feed the models. Sorry. Another point is that if we plot the number of earthquakes versus time since 1900 to the left and present to the right, it covers 126 years. So we plot all the magnitude more than 7.5 events. And what we see is that we are presently living, all our planet is living a period of where we encounter very large earthquakes. This is something unprecedented compared with what happened in the 60s, 50s, and 60s. We all know that the largest event occurred offshore South Chile in 1960. This is this one in red. But there were a lot of events that occurred during about 20 years at that time. So I call that the cluster 1 of mega events. But since 2004, with the Aceh event, offshore Sumatra and Andaman, we encountered a series of large, very large events, you know, in Maule and so on, Tohoku here. And the last one occurred last summer offshore Kamchatka in Russia, magnitude 8.7. So I don't know if this is the end of that cluster, but of course we are really aware of that, because that's probably why we are so interested by improving the models. So we considered that it was time to re-evaluate the spatial distribution of the energy with respect to plate kinematics along the subduction zones. So with some colleagues, we have built or revised the catalog of the subduction earthquake along the plate interfaces, and we focused on very large magnitudes, more than 7.5, and we covered the period from 1900 to present. And we called that catalog Subquake 2. These are the events with magnitudes. So you see in black the magnitude 9 events. There are only 4 during that time. In red, this is magnitude more than 8. And in green, this is between 7.5 and 8. All these events, so there are 207 events, produced energy, and 70% of the seismic energy released in the world were produced by these Subquake 2 events during that period. There are subduction interface events. But the two clusters, these two clusters, represent 60% of the total energy. So most of this energy is produced by these events. So we developed this catalog. So very briefly, this catalog consists, we have a probabilistic approach based on the uncertainties in location of the slab top. The slab is the subducting plate, and since we are focusing on the interface, we are looking at the top of the slab and the hypocenter. And then we checked every event, we validate with literature if it was considered by the specialist as a subduction event. So we did that, and we got 207 events. Then we selected rupture areas, parameters, based also on literature, models, and so on. So based on these documented ruptures, we derived scaling laws, and we provided rough estimates for undocumented ruptures based on the magnitude, because we wanted to have a rough estimate of the length of ruptures along the trenches. Of course, this is not very accurate. This is not accurate at all. At the same time, in parallel, we revisited the estimate of the tectonic loads. I mean, the slip that we can predict, that we can expect along subduction interface. And for that, we use a database that is available online called SubMap. And we revise plate kinematics at subduction interface. We have an estimate of the seismogenic zone geometry. And we got the expected slip along the subduction interface during the last 126 years. And then with this, we calculate and we look at the distribution of the seismic coupling. For us, this is the ratio of energy between what is the seismic slip from our database compared with the expected slip from SubMap. You know, if you have full coupling, then it is equal to 1 over the last 126 years. So we have mapped the whole subduction zones, and the first thing that we observe is the contrast in the seismogenic behavior, again, since 1900. Between subduction zones. So here I compare the two sides of Southwest Pacific. So you are of South Pacific. Here you are in the Southwest, and here you are in the Southeast Pacific. And you see that in the region of Tonga. So first I describe how it works. So you recognize the subduction zone, Tonga, Kermadec, and New Zealand here with Hikurangi. The patches, the colored patches are the ruptures, the stars are the epicenters, and the arrows, you have two arrows here that represent plate motion. The blue arrows represent the convergence between the main plates, the convergence rate, and the purple arrows represent the real slip along the subduction interface, because we account for the deformation of the upper plate, and we try to improve as much the real slip on the interface. And also another thing is the strip along the trench here, which is either colored or white. This is the seismic coupling, and you have the scale here. When it is white, it is 0. No event, no magnitude more than 7.5 events, subduction interface events occurred. And when it is colored, but it depends how many events you got. So you see that along this trench, for example, most of the trench is free of large events since 1900. And there are only 3 spots with moderate events, except here a magnitude 8 something, 8.1 that occurred recently in red. But all the others are, they are clustered along very restricted areas. On the other side of the Pacific, along the Chile margin, most of the margin was ruptured during the same time, with, of course, the very large event in South Chile here in black, but many magnitude 8 events in red here. You can observe the same contrast in the area of the Philippine Sea. If we look at the Japan, everybody knows that there were large events during that period of time, and same with the Kurils. But south of Japan, all around the Philippine Sea, you see that it resembles to the Tonga-Kermadec region. You know, very few areas were ruptured during that period of time. This is another focus on the region of the Kuril-Kamchatka. So you see that all the Kurils were ruptured. And especially this is the last event that occurred in August of last year, magnitude 8.7. And the rupture area here in dark red overlap almost totally the area of the previous event that occurred in 1952, magnitude 8.8. And all the epicenters, I mean the nucleation of these events occurred, many of them occurred offshore the Petropavlovsk, which is the main city in Kamchatka here. And the contrast with the Lesser Antilles is also very important. We didn't record any large events since 1900. There were some two events that occurred during the 19th century that are debated, but not since 1900. And yes, the last example, because I will not check all the subduction margin, but this is to illustrate the fact of the contrast. Yeah. So you see that here, the Aleutians were almost totally ruptured, and this is not the case of the Mediterranean Sea. At the end, if we look at the whole world, the subduction zone in the whole world, what we observe is a wide range of seismogenic behavior, both in space and time, and 2/3 of the margin's length have never been ruptured by those events since 1900. The problem is how to be sure that the period under consideration isn't too short. Of course, we all know that it is the case. So we have made two tests. The first test in two areas that are well known. The first test was in offshore Cascadia. Based on our time window, there were no seismic coupling. But there were a lot of paleoseismological investigations in the margin with using the distribution of turbidites that were triggered by events. And we have a series of events that were described with the latitude here back 10,000 years ago, back to 10,000 years ago. Based on this catalog by Chris Goldfinger and his group, based on this catalog, we have estimated the seismic coupling. And I'll go quickly. And blah, 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 blah. And we get a seismic coupling of 0.6 to 0.7. Far from zero since 1900. So, of course, we need to go back in the past to know what happened. If we look at the geodesy, so I present here the model, this is a block model of interseismic coupling based on the on-land stations here. And we see that the coupling is close to one near the trench offshore Cascadia. And there were a deployment of seafloor GNSS acoustic stations, and they show that the velocity of those stations, these 4 stations, close to the trench, are of the same order than the slip velocity, than the plate velocity. So it means that the coupling is full near the trench. So So this confirms the seismic coupling inferred from 10,000 years based on paleoseismological study. The second test was done in Nankai, which is probably the area in the world that is the most covered, the most monitored. And based on our study, this is all the events that happened since 1900. So our midterm seismic coupling varies between 0.3 to 0.5 in southwest Japan. So it means that at the maximum, half of the energy has been released, half of the energy stored during 126 years has been released during the same period. But we also have access to paleo events based on documents in Japan. And based on this, we have also a catalog of events back to 1,340 years. And based on this, we got a seismic coupling of 0.3, which is not far from what we have during the recent period. And we have also a lot of instruments, as I mentioned at the beginning. And based on the block model, we got a short-term seismic coupling of 0.4. And if we compare the short-term, few decades, 1 decade to 2 decades, mid-term and long-term, this is consistent. So for the Nankai margin, our observation is consistent with what happened in the past. So then, as a conclusion, very wide range of seismogenic behavior. 2/3 of the margins have not been ruptured by large events since 1900. There is, of course, a strong influence of the explored time window. And when the interface coupling derived from short-term geodetic studies is consistent with that inferred with released seismic energy over longer times, like in Nankai, it is likely close to the long-term value. So we have 4 types of margins. Those with segments that are relatively quiet during 1 or more centuries and that are capable of producing magnitude 9 events, that one are certainly very dangerous. Others that were largely ruptured since 1900, and like all these ones, okay. So we know that large earthquakes can occur, and the problem comes from the last 2 regions, with those that were moderately ruptured or not ruptured. For those, there are 2 groups, those where we know that paleo earthquakes are documented, like Mediterranean, Lesser Antilles, South Ryukyus, and others where we don't know much. Okay. Thank you.